All right, so we are doing DC circuits. Let me, so here is a circuit. So this is a circuit for the earbuds, okay. And the audio in is from, so you get your audio in from your phone, and there is the output in the earbuds, okay. And so the idea is what this circuit does is it amplifies signals, and it'll amplify the audio in and power the earbud speakers, okay. So that's what the circuit does, okay. Now what you're interested in generally in a circuit is, what you want to know is the current through every element, okay. In the circuit. So these are diodes, these are transistors, and these are capacitors, and these guys are resistors, as you know. So the circuit has resistors, capacitors, transistors, and diodes. Those are the four elements. And what you want to know is the current through every circuit. And this chapter will show you how to find the current through every element in the circuit. We will use something called Kirchhoff's laws to do that. Of course, we won't solve anything complicated like this. But anyway, you will learn the principles. Okay. Let's see. Let's make sure that there aren't other people waiting. All right, there seem to be other people waiting on. Hey, Ron, what kind of trouble did you have? I mean, it seems like Ty is waiting for the.
It just said that I was waiting for the host to let me in. Usually it's right away I get let in, but this time it wasn't letting me in.
Yeah,
right
but
away.
Okay, I'd stepped away, but there's another fellow waiting, and I don't know if he seems to have clicked the. Do you guys see two different URLs?
I just put in the meeting ID into the Zoom app on my computer and the password.
Okay.
Do you think he might have put in the URL for your office hours on accident, maybe?
Yeah, well, so that's. Yeah, that's the only thing I can think of. But Ron just said that he just joins the current meeting, I suppose. I don't know what's going on. Anyway, so this fella is waiting. Okay, let me take care of this guy first. I don't even know how to. All right, here he comes. Hey, Ty, what happened? Did you click on the wrong meeting? How come you were? Hello, Ty?
Hello?
Hello. What happened? Had you clicked the wrong office hours or something like that? I mean.
Oh, I clicked on the old email. It's fine. Don't worry.
Okay. All right. So we are interested in solving circuits like this. And when we say solving circuits like this, what it means is we want to know the current through every element in the circuit, okay? All right, so now if you had a single source like this and a circuit like this, these are just two resistors in series, then finding the current through this this circuit is easy. You just use Ohm's law, okay? So for instance, so I'll do a simple circuit. So here's a simple circuit. Um, and if this was a 12-volt battery, let's say, and this is 10 ohms, and this is 26 ohms. So the current through this circuit would be, current is, Ohm's law says it's voltage over resistance, and these are two resistors in series. You would just add their resistance. So the current would be 12 volts divided by 36 ohms. Okay. So 1/3 amps, 0.33 amps. Okay. So this is a very easy circuit to solve. And once you have the current, the power, so here's what you're interested in. Okay. The power dissipated in each resistor is I square R. Okay, so, or the power supplied to each element is I square R. So this is the reason why you want to know the current through each element. It tells you how brightly it is glowing, or how much power is being delivered to that device or that element in the circuit. Okay. And so that's why you want to know the current through each element in the circuit. And that's what we'll be solving for. Okay. Now, so this one is easy to do. Now you'll see that, so let me show you a circuit where, so here's a circuit. It has multiple sources. And now you can't use just, you can't use Ohm's law to find the current through each element. Okay. So the way, and we'll learn the technique to solving it. And you see, what we've done is we've labeled the current through each arm by an unknown. So the current through this arm in the circuit is I1. The current through this arm is I2. And the current through this arm is I3. So solving a circuit would mean solving for these three unknowns. Okay. And so we'll learn the two Kirchhoff's rules that help us solve these for these unknowns. And that's what solving a circuit means. Okay. So we'll get to that. So now what this diagram is showing you is, we talked about it, it introduces electromotive force. So for instance, here's a battery and here's a resistor connected to the battery. And what we mentioned was, what the battery does is it converts some kind of chemical energy and raises charge from low potential to high potential. So it increases the potential energy of a charge. Okay. And then this charge loses its potential energy when it goes through an element in the circuit. So for instance, this could be a toaster, and that electrical energy is converted to heat and light in the toaster. Okay. All right, so a battery is our generator is a charge pump. It moves charge uphill from a lower potential to a higher potential by converting some other form of energy to electrical energy. Okay. So when you buy a battery, what you have done is you paid for a certain amount of energy. That's what you've done. Okay. A certain amount of energy in a convenient form. The EMF of the battery, or also known as the electromotive force of the battery, often denoted by script T like this, of a battery is the maximum voltage the battery can provide. And oftentimes these, you'll see in circuits, batteries written like so. And this is an ideal battery. And this battery provides an 18-volt voltage. And that is the EMF of the battery. Okay. Now we'll show you a battery with internal resistance in a second. Okay, so the maximum voltage that the battery can provide is the EMF of the battery. In this case, it's 18 volts. Here's the more realistic battery. So here is the battery, and this is what is called the internal resistance of the battery. Okay. Now, the voltage you see, your device will see, is the voltage outside the battery. Okay. And this is called the terminal voltage. Okay. So the voltage between point B and point A is called the terminal voltage. This is the load that you've connected to the battery. Okay. And this formula tells you the terminal voltage, VB minus VA, is the EMF of the battery minus the current drawn times the internal resistance. So for instance, let's say this is a light bulb you connected, and the resistance of this is 10 ohms. And if the internal resistance is 1 ohm, okay, and if this battery was a 1.5 volt battery, what you'll see is 10% less. What you would see is the terminal voltage would be 1.35 volts. So that's all you get to see, 1.35 volts. If this was 1% of the internal resistance was 1% of the load, then you'll see 99% of the EMF. Okay. Anyway, so roughly that's what this is. Okay, so the terminal voltage VB, the voltage at point B minus voltage at point A, is the EMF of the battery minus the drop in voltage because of the internal resistance. Okay. Most times we won't mention internal resistance, we'll neglect it, and in most circuits all we'll draw as an ideal EMF, okay, just the voltage of the battery. But anyway, this is what you need to be aware of this. And so when a battery dies, you can think of a battery dying as the internal resistance going to infinity, internal resistance being large, and then you don't see any voltage outside, and you can draw very little current from it. So that's a battery dying. All right, here again, so the current in the circuit, Kavi beta. So the current in the circuit is the EMF of the battery divided by the total resistance in the battery, in the circuit, which is R plus R. The power dissipated in the circuit is I square R, which is the power dissipated in the load, plus I square R, little r, which is the power dissipated in the internal resistance of the battery. Okay, so you see this is wasted energy. This is what this is the power delivered to the load. This is what you want. Okay, so you want the internal resistance to be as small as possible, negligible, hopefully. Okay. All right, so now here are resistors connected in series. So if you connect two light bulbs like that to a battery, these are light bulbs are essentially resistors, and they're specialized resistors, and they are connected in series. Now, one of the things we're interested in is what is the equivalent resistance? What is the equivalent resistance of these two guys? So when resistors are connected in series, the equivalent resistance is just the sum of the resistors. So if you have a bunch of them, the equivalent resistance is just the sum of the resistors. And you see the current through each resistor is the same. Okay. However, the more resistors you have, the lower the current from a given battery, okay, for a given voltage. Here are resistors connected in parallel. So now each resistor sees the same voltage. Okay. And also we will be interested in the equivalent resistance. What's the equivalent resistance of these two resistors? Okay. So the equivalent resistance is given by 1 over the inverse of the equivalent resistance is 1 over R1 plus 1 over R2 and so on. Okay. So it turns out that so if you look at this equation, let's say there are only two resistors. This guy is positive, this guy is positive. So this number is bigger than either one of those numbers. Okay. Now for this guy to be bigger than either one of those numbers, this guy has to be smaller than either one of them. Okay. So when you connect resistors in parallel, what you get is an equivalent resistance that's smaller than any of those guys. Okay. So, so when you have a bunch of resistors and you need a bigger resistor, you connect them in series. And when you have a bunch of resistors and you want a smaller resistor, you would connect them in parallel to get a smaller resistor. Okay. Kavi beta, you have to turn it down. Okay, so these are resistors in parallel. Okay. Now, All right, so now here's a fun problem. It's a rather interesting problem. So imagine an infinite ladder of resistors and assume each one of them is 1 ohm. Okay, so try and find what is the equivalent resistance of this this infinite ladder. Okay, so again, let me draw this for you guys just to make sure you guys understand this. Again, this is just a fun thing, so for you guys to try at home. So 1 ohm, 1 ohm. Again. One. This goes. So what is the value of R is the question. Okay. So let me give you a hint. So this is 1 ohm, this is 1 ohm. Let's say this is some effective value. So, but since there's stuff connected in parallel to that, that has to be less than 1. So R, so here I'm giving you this hint, R has to be some value between 2 and 3 ohms. Okay. Now, if that problem interests you, find the value of R. What is the value of R? Okay. Just a fun problem. All right, now we'll get to Kirchhoff's rules. Okay, so what we are interested in is you'll have circuits like this with multiple sources and multiple elements. Right now, this has only resistors and so on, but you can have, as you saw in the original circuit, you can have in the example at the beginning, you can have transistors, diodes, and all kinds of elements. And what you want is the current through each element in the circuit. And that's what you're interested in. And Kirchhoff's rules will help you solve circuits problems like this. Okay. So for instance, in this problem, there are 3 unknown currents, I1, I2, and I3. I1 is the current through this arm, I2 is the current through this arm, and I3 is the current through this arm. And we want to be able to solve for these unknowns. Okay. All right, before I proceed, I am going to pause for a second. I'll let you guys ask questions.